module 3, if you look at this is done, and this one yesterday some 30% done. We should continue this later. Why there is some reason, you understand it. Now this one we shall start now. Correct. So this is the agenda today. We will teach you. I will teach you the elimination models theory in this hour. That is within 9:30. By 10:50 to 11:50, there is an implementation of this elimination model called as teapot program or the lab program number 6. That is the reason I have skipped this for a moment. All right, moving on. This is that elimination models. Now understand, guys, for to see an image, what are the prerequisites? One is the projection rays, or I can say the incident ray should meet the reflected ray. Second point, lighting should be proper. Third one, you remember in my class I always used to say, why am I not seeing the blapper for that instance? So the point is, my rays, my incident rays would never meet the reflected rays, would never reach that place, and yeah, the first point itself fails. That's the reason I don't see those distant places. So to see any image, the rays should meet and the lighting should be proper. And of course, in other words, for this, I can say projection should be proper. Projection should be proper. So in the sense, there are two ways, there are two types of projections. One is or one is called as parallel projections, and the second one is called as perspective projection. So in parallel we have orthographic, oblique, making treatment. In perspective, we have 1 point, 2 point, 3 point, frustum, many things. So by default, this is this gets applied. That is parallel projection and orthographic projection. That is the reason by default, even though you don't write this, you will get it. That is the reason we write this ortho. So even if you don't write this, it assumes the default projection. And if you want to change your near, far, left, right, and all, you should, by default, you need to change the parameters. So this, assuming that this is there, that is the projection is proper. And if I don't do this second concept, that is, if I don't set my lighting properties, I will not see my image. That is the crux of my today's topic. So to see an image, for example, let us say I will run this program and you are seeing this particular teapot image. So if you are seeing this, means I should be done with this and I should also be done with this. So if I don't do this, for example, let me say I will not do this. I will not enable my lighting. So if you run this, you will see you are not seeing your image. So in order to see the image, lighting should be proper. And you can ask me, in the previous programs, we didn't do all this. Right? So even though we have not done that, we only saw an artificial image. In order to see a realistic image, you need to see you need to turn on your lighting properties. That is what is today's topic. That is called as illumination models. You'll understand all those lighting properties in a moment. So you can see all these codes here: GL shade model, smooth lighting, light zero, light FV. You can see here GL position, GL diffuse, triangle, normal, all these stuff. So the first question you should get is, what is going on here? So we shall come back to this slide once we are done with these properties. So why lighting, if you can ask me, to take any 3D picture or 2D picture without lighting, it will look something like this, kind of an artificial image. So with lighting, you can see here, I have taken care of all the lighting properties. The camera is somewhere here. So these surfaces will be illuminated well, and these surfaces, I can say this as shadow and all. So some particles are bright and some particles are dim. So this is the 3D image with lighting. So which looks more realistic? So the right hand side, the 3D image with the lighting, that looks more realistic. So if you don't turn on your lighting properties, this is what you'll get, and this is what we got all these days. You take first program, line program, you take second one, that is a triangle rotation, you take coincidental, and all these were artificial outputs, something like this. So we didn't take care about lighting in those programs. So if you take care about lighting, you will get something realistic image, something like this. All right, so one more image, 3D without lighting. This is how it looks, and with lighting, this is how it looks. Just to show you the importance of lighting. Well, in real world also, we have three types of lighting. One is called as ambient light, one is called as diffusion, one is called specular. Now, what do you mean by ambient light? The light which is caused due to the ambience. For example, due to sunlight, we can see an image. Due to the reflections of other properties, other metals or other items around you, some light will be reflected from them. So due to the ambience, you will get some light that is called as ambient light. Diffusion means once you turn on your light sources. For example, in real world, if you can turn on your tube light or any other light source, if you project at this angle, these surfaces will be diffused. In the sense, the light rays will be more on these. That means an even surface, equal proportion, equal distribution of light happens around at this particular point. That is called diffusion. Means it just diffuses the light rays. It just spreads the light rays. So what do you mean by specular is the moment you turn on your light and project onto it, some portions will be having a lot of shininess. Some portions, some pixels will be highlighted very much. So the shininess property is called as specular property. I'll repeat: the ambience light, the light caused due to the ambience is called ambient. So for example, sunlight. Diffusion is your light sources, tube light, whatever torch in your mobile screen, mobile torch, the camera torch, all the stuffs first to diffusion, and some pixels will be highlighted much. That is the shininess. So this is called as specularity. Now, just to give you an example, what are these? One second. You can see this. Yeah. You can. What do you mean by shininess? For example, if you take this image, the below portions, there is the dim guys. These are ambience, and these somewhat bright. These are diffusion, and these white patches. These are due to specularity. You can take this any steel items. You can see this bright spots. These are specular, and the other things, the kind of bright pixels, they are due to diffusion, and those dim lights, them dim pixels somewhere in the bottom, you can see here in the bottom, these are due to your ambience. So just to give you an idea about how exactly ambient looks like in real world. I'm seeing diffusion looks like, and specularity looks like. So ambience, yeah, just to give you some perspective via textbook definitions, this is how textbook definitions look like. Ambience means surface exposed to indirect light reflected from nearby objects. Diffusion is a reflection of incident light with equal intensity. That's what I use the word called spreading. With equal intensity in all directions, depends on surface properties. Surface properties, there are two types. There are two properties. One is called rough surface, one is called smooth surface. We'll come back to that later. Specularity is near total of the incident light around reflection angle. That means the moment you project it, there goes this. Some pixels will get more light due to the incident angle around the reflection theta. So that is the shininess coefficient. All right. So in this diagram, you will understand if I have more specularity, that is some pixels whichever are highlighted. Only those guys I'll see. The other guys I will not see. On the other hand, if you look at this one, that is the top left, I have only more diffusion, whereas the light has been spread equally. I'm not seeing any bright spots. So a perfect image should look like this top right corner, top right. That is equal amount of distribution, equal amount of diffusion and equal amount of specular. Of course, equal amount of ambience also should come into picture, which will be given here. Now, you take any image, if you turn on only ambient properties. What do I mean by turning on only ambient properties is, for example, look at this code. You can see if I turn on, that means if I comment out these guys, means I'm turning on only ambient light. I might get an image something like this. You can see only ambient light, no shading, no shadows, all the stuff. This is, I mean to say, you will get an image, but the point is the image will not look natural. The image will look very artificial. That means if you don't take care about diffusion, if you don't take care about specularity, shininess, and ambientness, that means if you don't take care about all these four put together, your image will look very very artificial. Now uncomment all those, and now you run it, you will understand how exactly an image looks very natural to you. You can see uh, here in the beaker, you this part looks. What is this part? This is specular part. You can see these guys and also these guys, the legs. You can see some dim pixels here. So these pixels, the dim pixels are due to your ambience, and you can see somewhat bright pixels here, and all. This is due to specularity, and the beaker, somewhat white pixels here, that is your shines. So that means if you take care about all these ambient light, diffusion light, specular light, and shininess, your image looks very natural. That is what I'm trying to say. So just to give you some more perspective, let's say there's an image, and if you have taken care about only ambient light, this is how it looks. And if you have taken care only about diffusion, this is how it looks. Specularity means this is how it looks. That is only the bright portions, the shininess ways. And a perfect image should look like this, in the sense you should have taken care of ambience, diffusion, and specularity, and this is how your natural image should look like. In other words, natural image comes with equal proportion of ambience, diffusion, and specularity. This is what I mean by elimination models, light sources. Now, coming to some mathematics about this, what are the various light sources we have? What do I mean by light sources is, you can see in my program, yeah, you can see here, GL light 0. Like this, I can write GL light 1, light 2, light 3, light 4, up to light 7. So what do you mean? What do you mean by light sources? If you can ask me, for example, if you turn on your tube light, that is your light source number 1. If you take your camera, if you take your mobile phone and turn on the torch, that becomes your light source number 2. Sun is light source number 3. 3. If you turn on one more tube light, it becomes light source number 4. Turn on your web camera has some light, that becomes light source number 5. Like this, various light sources. Light source, put it in textbook words, it's an object that radiates energy: sun, lamp, globe, sky, tube light, torchlight, or whatever. And of course, intensity, every light source has some intensity, and of course that intensity can be measured in terms of RGB, red, green, blue. And if you give me equal proportions of red, green, blue, you'll definitely get white light. And if you don't give me these, you'll get black light. That means you will not see any color at all. Now, there is something called as point light source. That means you will have a tube light here, and you turn on, equal amount of rays goes out. That is called as equal diffusion as well. Now, this is the concept of sunlight, point source. Sun is here. This is the light radiations coming up from one point source. You can see here all these are. I mean, once I talk about perspective projection, you see sun is nothing but perspective projection. Anyway, the V is your direction and I is your intensity. Point source example is sunlight. Attenuation is something called as loss. For example, if you go to sun, if you take this example, there is heavy light here, and as and when the distance increases, slowly the light intensity gets decreased. For example, you turn on your tube light, you go nearer to the tube light, you can see more intensity. You come farther to the tube light, you can see the intensity will be less. So the intensity is more means less attenuation. Attenuation basically means loss. The English word of attenuation is loss. So the more closer you go to the light source, there is less loss, and the less closer you go to the light source, there is more loss. So how do you put it in terms of mathematics? The energy from a point light source falls off proportional to 1 by d square. D is the distance. That means more, for example, if you take this case itself, energy, I will write it as energy is equal to 1 by d square, or I can write and intensity is equal to 1 by d square. That means there is 1 by d square. D is distance, that is in the denominator. More is the denominator, that is more is the d, less is the attenuation, less is the intensity. Intensity is equal to 1 by d square. Denominator, if you increase, the left hand guy will be decreased. It means intensity will be less if the denominator, that is 1 by d square, that is d, if that is more. On the other hand, intensity is equal to 1 by d square if d is less, that is if the denominator is less. That means if the distance is less, obviously the left hand side, that is intensity, will be more. Just to put it in perspective. All right. Now you can see here, actually the intensity is 1 by d square, that's it. But 1 by d square, it is very intense. So what we will do is 1 by d square means I can write 1 by a naught into d square. A naught in the sense only one light source. So what about tube light? What about other lights? So what I'll do is I will add some linear equations in the denominator. Something like this: a naught into d to the power 0. D to the power 0 is 1. That is why I have done a naught. A naught is one light source into that distance plus a1. A1 is one more light source into d to the power of 1. That's distance. A2 is one more light source powered by into that particular distance. So if you keep on adding like this is how your attenuation comes into picture. Okay. So now you can see here, yeah, these are the various light sources, and you can have as many as light sources, and all these distances, this you can consider as a1, and this can be your distance. This can be considered as a2. This can be your distance. So how exactly your object gets eliminated is, if you want to calculate the intensity of the whole environment, you can use this formula. So what is wrong with this formula is, you can see it is very linear. So the final formula will be something like this. Now, if the source is at infinity, that means let us say sun, very, very far, and my f of d, that is the intensity, and the attenuation will be 1. Means what? It is 1 divided by 1, that is 100% loss. This is, I'm talking about loss now. Loss, that is attenuation means loss. Loss is equal to 1 means 100%. When it can be 1 is numerator by denominator is 1. Numerator is 1. Denominator is also 1. Means source is at infinity. So if the source is at infinity, the loss is 100%. That means I cannot see at all. That means, you, for example, you take your tube light and fix at, let's say, 10th floor, and you are now at the first floor. So in the tube light is at the 10th floor, that is source is at the infinity, and your loss is 100%. Means you cannot see at all. On the other hand, get the tube light in your first floor. So this is the equation. 1 by this, the same equation, 1 by a1 plus a1d plus a2d square. This equation. So the good fix is you should take care about the two cases. One is if the tube light is at the 10th floor, you will not see anything. That means you will see 100% loss. Once your tube light is at your distance, that is the local source, and this formula holds good. All right. To sum it up, energy is of course distributed by 1 by d square. 1 by d square in practical it is too aggressive. That is why we have light sources. If the light source is at infinity, no damping, means heavy loss, 100% loss. Now radical intensity is 1 by d square. That is what we did, and 1 by d square produces too much of intensity variations. That is why we are adding linear terms. The remedy is linear terms. That is a naught plus a1d to the power of 1, a2d square plus a3d cube plus a4 to the power of 4. So as an, I mean, the more is your light source, the denominator you can just keep on adding linear. Yes. All right. So another problem is the same whatever we have taken this. This is just a summary of whatever we have discussed. All right. Now there is something called a spotlight effects. You can see if this is the light source, and the direction, that is the intensity light source, the light rays will go in this direction. Now it forms a cube, and there can be an object something like this. For example, you take let's say a cube object here, any 3D object, any 3D or 2D object, and let's say you have to find out the intensity which is at this point called Q, and the light source is at P, and you are pointing your tube light at this direction, so the light rays goes this direction. Also, some of the light rays fall on Q, fall on this point, for this point, fall on this point. How exactly you can put it in mathematics? Physics is there is a point source, it forms a cube, a cone nature, and wherever you point your tube light or light source, it goes to in this direction, forming the θ1. And if you want to calculate what is the light intensity applied at this point called Q, the formula is something like this. This angle is alpha, and if you want to know whether Q is illuminated or not, the formula is something like this. Cos alpha should be greater than cos of θ1. You can see here, light is primarily sent in the direction of V light, and you want to know whether Q, that is this point, is illuminated or not. That means whether this Q is shown or not. So the formula is this angle should be more than this angle. Cosine of this alpha should be greater than cosine of theta. Then only you can see Q. Let us take the contrary case. Let us say this alpha is less and this theta is more. That means you have taken your tube light into this direction. In the sense, θ1 is more and this alpha is less. So in that case, chances of you seeing Q will be very, very less. Let us take the contrary. You take your tube light and point directly to Q. In that case, alpha will be more and theta will be very less. So chances of you seeing Q is very, very high. So put it in generic terms. A point source is here. The light goes in this direction, forming two angles. That is the cone angle called the theta 1 and the reflected angle called alpha. So you can see this Q pixel, in which case the cosine angle of alpha should be greater than theta 1. Now put it in other words, that is called your dot matrix vector words. Q minus P, that is the distance between this and this, divided by the vector into your V light. Cos alpha is apparently this now. So put it in dot matrix, the distance divided by the vector into this V light should be greater than cos theta 1. Then only you can say your Q gets eliminated. Now, if you take care about the distance, that is, that is this point, you will get bright light, something like this. That is, your Q gets eliminated. Now, let's say your intensity, of course, decreases with increasing angle of alpha. Of course, if this gets increased, means to say your illumination light should be equal to cos of n power cos to the power n alpha I. Means that is, I am putting this equation in one more way. See, one equation is cos alpha should be greater than cos theta. That is, this angle should be more than this angle. Second way to put this is in the dot matrix vector Q minus P divided by vector of Q minus P into V light should be greater than cos theta 1. One more way is something like this. Of course, the intensity will decrease with this. So you can see here, the larger the n, here, cos square alpha, cos to the power cube alpha, cos to the power 4 alpha. If you keep on increasing this, if alpha goes on, keeps on increasing like this, your intensity, the intensity will be decreased. Means if this gets increased, obviously Q's intensity will be decreased. That is, I'm just putting it in different terms. One is the vector one is this one. So the larger the n, the stronger the light decreases. One more way, something like this. For example, if you take care about this, that is, everything is proper, you will get something like this. That is, the light reflects all the way. And if you don't take care well, that is, if the cos of alpha is not greater than cos theta, that is, your n is increasing. So you will see the light is not getting spread uniformly. One more way, there is this light source, you need to project this, and this is your theta, this is your alpha. Of course, cos alpha should be greater than cos theta. Now, to put it in generic terms, I can write the loss formula something like this. When the source is not the spotlight, you will get 100% loss. 1 by denominator is 1. I am talking now about attenuation, that is the loss. That is, source is not a spotlight. Means somewhere you are keeping in 10th floor tube light, and the first floor you have the object pyramid, and you will not see the object. Now, if the cos alpha is less than cos theta, means, see guys, understand, the first one says source not a spotlight. Spotlight means the tube light is in the 10th floor and the pyramid is in the first floor. There is 100% loss because tube light is somewhere else. Now the second one is tube light is in the first floor, pyramid is also in the first floor, but the light source, that is the tube light, you have not projected onto the pyramid. That is cos alpha less than cos theta. You remember this slide? This one? Yeah. What he says? This angle cos alpha should be greater than cos theta. Then only you will see your pyramid, your cube. Now, if cos alpha, on the contrary, the cos alpha is less than cos theta, you will not see this cube. That is what I am putting here. If cos alpha is less than cos theta, even though your tube light is in the first floor, your pyramid is also in the first floor, you will not see anything. That is your zero. Otherwise, means what? Tube light and pyramid both are in the first floor, and you have projected this tube light in some direction about your pyramid. The chances of you seeing that particular portion is cos to the power alpha. Cos to the power alpha is this side. Cos to the power of n alpha. Cos alpha is also can be written as V object into V light. Now, I talked about in the previous slides, I told you that there are two types of surfaces, right? One is called as rough surface, one is called as smooth surface. Now, if the surface is smooth, you will see the reflections are same. You know, if you, for example, if you project this red light onto this green surface, and if that green surface happens to be smooth, you can see all my reflections are equal. This is called as smooth reflection, and this is what you mean by total reflection. Now, this will not happen in real time because you cannot expect all the time the surface to be very smooth. So this is, I can say, this is artificial. Now, on the other hand, this is natural. You can see here this green surface, purple surface, and the blue surface. These are all rough surfaces. You can see one incident light, it will now cause at, let's say, 68 degrees. Second one, it will now cause at 43 degrees. That is, this is the deflection angle. So that is how light gets diffused or spread across all the surface, and that is apparently your diffusion reflection. So what I'm talking about this slide is there are two types of surface. One is called rough surface, one is called smooth surface. Smooth surface is artificial. If you code it, you will get your image artificially, and you should consider your, I mean, if you want to have your natural realistic image, you should consider diffusion reflection. That is, your surface should be very rough. How to get this? How to make sure the surface is rough? How to make sure the diffusion happens? How to make sure specularity, shininess coefficient? How to increase the shininess coefficient? For example, talking about this. You can see how to increase the intensity, how to increase the shininess, how to use this ambience. What do you mean by diffusion, specularity? What happens if you increase or decrease shininess? What happens if you increase or decrease intensity? All these guys, whatever theory I'm doing now, will be taken care in my coding part by 10:50 a.m. today. Okay. So basic illumination is of course ambient light, which determines the brightness. That is your sunlight and all. And if you want to have, if you want to spread your light across all the uniform objects, you should have diffusion reflections. Now, if you ask me what is ambient light in terms of mathematics, all these while we discussed theory about it, the mathematics angle is something like this. Understand, guys, in the university question paper, they will give you these kinds of problems. They'll give you intensity IA, and they'll ask you to calculate ambient light intensity, diffusion light intensity. There are three formulas. For ambience, there is one formula. For diffusion, there is one more formula. All right. So now, I mean, all this while we talked about theory, now we'll talk about mathematics. Now, as you know, ambient light depends on the surface, whether that is rough surface or smooth surface. In the sense, I can write IA, that is ambient intensity, is directly proportional to K. Ambient light is directly proportional to intensity of IA, and it also depends on rough surface or smooth surface. So if you eliminate the direct proportional symbol, you can write this equation. So I ambient is equal to Ka times the intensity of ambient light. So this is the equation of your ambient light. So if I want to calculate what is the ambience of the entire environment, you should give me this. What is the intensity of ambient light and what is the surface? Now the point is, ambient light itself is not enough. I should require diffusion as well. Right? You can see all this. So if this is the IL is the incident light, and if this is the surface, and if you can draw a normal, that is a perpendicular line, and this forms one angle and this forms one more angle. So for a light source, since I have to here I have calculated ambience, and you can I already talked about this, right? If you want to see a naturalistic image, you should calculate intensity of ambience, diffusion, and specularity. Ambient intensity is this formula. Diffusion intensity is this. So it is intensity illumination IL in the sense light source into cos theta into KD. That is the reflection parameter called KD. That is your intensity of diffusion. Intensity of ambience is KAIA. Intensity of diffusion is KD. That is the diffusion reflection parameter into intensity of your light source into cos theta. Theta in the sense this one. This one. All right. Now put it in other words. That is the dot matrix words. Diffusion is N into L. N in the sense this one. N. This is your light. Put it in other words. P source minus P surface. You remember we did this Q minus P thing in the last couple of minutes back. So the same thing. P source minus P surface divided by the dimension of that. The distance of it. Same thing. In replace this with KDIL cos theta, KDIL cos theta. Cos theta can be written as N into L. That is the dot matrix of normal into the intensity of light. So if cos alpha, that is what we discussed. If cos alpha is greater than 0, you will definitely see the object. If cos alpha, cos theta, cos of that angle, if that is less than 0, you will not at all see the object. Just to put it in other words. Now, let us, since we have now understood ambience and diffusion, let us combine both. So KAIA is your ambience, KDIL cos theta, KDIL NL is your diffusion. In fact, in my next slide, coming in mathematics, I should now combine ambience, diffusion plus specularity. So since we have not done specularity, since we are done with ambience and diffusion, let us put it in a nice way. So your diffusion reflection, that is the intensity of your diffusion, is equal to, of course, ambience plus diffusion. In which case, if my angle, that is the cos theta, is greater than 0. Now, if cos theta is less than 0, means I can see only my ambience plus diffusion is, since the diffusion is 0, I can write KAIA plus 0. That is the reason I'm writing KAIA. In which case, if my cos theta, that is N into L, the normal vector into light intensity vector, if that happens to be less than 0, that is, if this is less than 0, the entire thing becomes 0. So KAIA plus 0 is KAIA. So if you can give me cos theta is greater than 0, that is, provide a proper light source, my diffusion reflection will be ambience plus diffusion. Now this is not the final thing. We have not considered specularity. So once I'm done with specularity, you can then combine all these ambience plus diffusion plus specularity. So if there is no diffusion, means only ambience. You can see here in this case, take the bottom right, more diffusion means N and L greater than 0, more diffusion, less ambience. So this is how you will get. On the other hand, less diffusion, more ambient. That is your N and L less than 0 in this case. Top left. Bottom right is the equation number 1 uh, having more diffusion. And the equation number 2 is your top left, wherein there is no diffusion at all. N and L, N into L is less than 0. So you will have only KAI, that is only your ambient light. So what should be your perfect image? Perfect image should be your top right. That is some amount of ambience and some realistic amounts of diffusion. So this is how we should get any image. And of course, this is not natural. This is not natural. Why? Because we have not taken care about specularity. We have taken care about only ambience and diffusion. So the moment I talk about specularity in my next class, you will understand this particular top right image looks even more realistic and courtesy specularity. So this specular reflection, and there is a theory called Phong model. There are many models. One is called Gerard model, smooth model, and all. So there is a in the camera, in the realistic computer graphics, there is one specular one reflection model called Phong model, so which we shall see in the next class. uh, all these while, whatever we discussed, let us quickly sum it up quickly. Various, the you view here various light sources. And so you can view directly. Reflection means due to the reflection of other objects. There are various light sources. Yeah, point light, direction light, spotlight, ambient light, all these. So various light sources, reflection. This is a normal, incident ray, refracted ray. So smooth surface. I'm just brushing up whatever we discussed. Smooth surface means equal amount of intensity, equal amount of theta we saw, and this is artificial. This will never happen. We will only deal with rough surfaces. Smooth surfaces means you can see here all these thetas are equal. Rough surface thetas are, I mean, the angle is different. This is uh, realistic. Now specular reflection, diffusion. Specular reflection means the surface is smooth, and diffusion, inversion surface. This is how the reflection happens. So this intensity, because of all these, you can see direct lighting, direct plus indirect lighting. That is diffusion plus ambience. This is how the realistic model looks like. So all these, you can see, yeah, the realistic model will be equal to ambience plus diffusion plus specular. I'm just brushing up. Ambient light is what is your indirect lighting. That is, you don't turn on your tube lights, you still see some image. That is the courtesy due to the reflection of other objects and your sunlight. So this is what is your ambient property, IA into Ka, and this is your diffusion component, Kd cos theta, and this is what we saw: more intensity, more ambience, more diffusion, and just to give you one idea about how specularity looks like, because these are the bright spots, these are the specular, and these are the diffusion, and the bottom one are your ambience. So this specularity we have not discussed. We will discuss it in the next class. Now, any doubts as such? We have done till we are uh, done with ambient and diffusion. Specularity we shall see in the next class. Now, this is enough for us to start this program in my 1050 class. All right. Now, the last bit. We also show this. Yeah, only diffusion plus specular. I'll talk about specular in the next class. Now, yeah, remember this. Yeah, all these, and the question was what is going on here. So I believe you got the answer. You can see light zeros means your light sources, smooth means smooth shading, These two are enabling the light properties and the light source, position, diffusion, and some 50% knowledge you're able to understand when compared to, I mean, like 1 year, 1 hour back, it was totally Greek and Latin. Now we have understood what do you mean by diffusion, what do you mean by specularity, what do you mean by light source, lighting, and smooth shading, rough shading. So this is enough for me to start this lab program. You can see ambience, diffusion, specularity, and shininess. Specularity, even though I have not taught you mathematically, I have taught you orally, that is the shininess concept. So this is enough for me to start my 1050 class. Please don't miss that class. I will show you line by line. I will keep, breakpoints. That is, I will keep my flush for every object. You can see here, guys. I'll end my discussion in 1 minute. You can see this. This is not coming all of a sudden. These are all various properties, but there are 4 legs. Each leg comes one by one. So how exactly it comes one by one? What do you mean by all these? I will start this discussion in my lab class, that is 1050. 1050 to 11:45. I'll do this program. In 11:50, you have your Ketima madam's class. All right. So I believe you have understood the theory behind this, and now please, we are done with this first hour class. Now please put your attendance here itself. You can write your USN and say yes, something like that. So you can please drop your attendance here itself. Uh, Thank you for watching, and have a nice time. Please drop your attendance. Thanks. In the meanwhile, if you have any doubt, you can turn on your mic and you can ask. Quickly, please mark your attendance. You have second hour class now. I think cryptography. Yes, of course, you can use lighting for 2D images. In fact, that 2D image will now look more realistic. In your mini projects and all, you will definitely use all this. Please mark only your attendance.